Good morning, everyone. Thanks for joining us this morning. Alex Meany is back with a part four, basically. He's run us through the load calculation and system selection. And last Friday, we learned how, unlike commercial, residential duct design is somewhat backwards. Today, we're doing failure is inevitable, but we're going to learn how to fail on paper rather than failing in the field. My name's Jason Vandiver. I'm an Energy Code Program Manager for Spear. We have another HVAC related webinar over ventilation coming up on June 5th with Tom Morrell of QFresh. We'll be doing that one for us. Little housekeeping, if you click on the Q&A panel, you can type in your questions. We'll hold questions till the end. Mariel will send out a course evaluation after the webinar this morning. We are an ICC preferred provider, so if you want your ICC CEUs, simply fill out that course evaluation and you will get your ICC CEUs. I guess that's it. I hope everyone has some big plans this weekend. Finally getting the boat out on the lake myself, so hope to do a little surfing. I hope you guys are going to have some fun too. And with that, I will turn it over to Alex Meany, who's a senior trainer with RightSoft. Really sharp guy. He definitely knows what he's talking about, so I hope you enjoy it. And take it away, Alex.
All right. Thank you, Jason. Sorry, guys. Jason usually has an intro slide, so I didn't put my contact info on here. I'll put it up at the end in case anybody wants to get a hold of us. So yeah, failure is inevitable, and how to fail on paper or preferably on a computer screen so you don't have to fail in the field. It's a little attention grabbing. It's not as negative as it sounds, but let's go through an actual duct design. That's actually what we're planning on doing here. This is the process of doing a real duct design. I just have a couple of quick slides to kind of go over why we, don't want to just wing this and actually want to design something the right way. So a lot of what we are dealing with, and I apologize in advance, some of the slides are a little number heavy. You don't need to be like staring at the numbers. I will, run my cursor across the screen with my little laser pointer here. And I'll read anything you need to know. So don't let it overwhelm you. And there's only a few of them. So the rule of thumb thing is just, it's what dooms us all, like from the get-go, right? I find personally when they teach a lot of HVAC professionals, when they teach them design, they teach them sort of crappy rules of thumb. And when they teach them service, they teach them how things work, right? Because you can, and we trust people to design systems with like these, just like 400 CFM per ton and 0.5 inches of static on whatever the manufacturer's shipping speed is, and this, that, and the other thing, and everything will work just great. I've been teaching classes on how to design duct systems and just had contractors interrupt me because I'm telling people to look things up, and they're like, "Oh, you don't have to look this up. It's always going to be 0.5 at medium speed or whatever the speed that the manufacturer ships at." And the guy who interrupted me, he believed it. You know what I mean? He wasn't just trying to be a punk. He was like, "Wow, this guy's really into numbers. We should take it easy on these folks. Just tell them to use 0.5." And I think that might have been. I've been told by people who in the know who tell me that was never actually true. I think it was probably more true back in the day, though, than it is now. It's actually really important that you not trust those things, because service people don't do that kind of thing. Service people, look things up, right? You gotta, you gotta know the outdoor temperature and the indoor humidity, and you gotta test things to know how things work. So I like to use that, 0.5, for nominal tonnage at medium speed as a good demonstration here. Because if I trust that the 2-ton blower, these are real blowers. I'm using furnaces here. I could have just as easily used air handlers. They're not identical furnaces and air handlers. But the point is made either way. I know in some markets in Texas, furnaces aren't very popular. I know in other markets in Texas, furnaces are very popular. So I just went with furnaces because I happen to have some data handy, right? But if I trust that 800 CFM is going to come out of a 2-ton blower at 0.5 inches of static, well, okay, well, here's my 2-ton blower, and here's medium speed, and 800 CFM happens about here, and so that's 0.7 inches of static. Actually, this 2-ton blower is pretty powerful. It's going to handle, it's going to deliver all that air past all that static right there. And actually, if I was running it at 0.5, I'd get 860 CFM, which, like, so you get more air. Who cares? Well, actually, more air makes it harder for a system to remove moisture. And if I'm in Corpus or I'm in some area where moisture removal is my biggest problem, getting extra air is maybe not such a great idea, right? And let's take that same, all right, medium speed, right? Medium speed. Let's look for 1,200 CFM out of the 3-ton, and you can't get it at all. Medium speed on the 2-ton, super powerful. Medium speed on the 3-ton, I can't even sniff 1,200 CFM of air. Doesn't happen, right? Under no circumstances will this fan, these, by the way, and I love this fact, I mean, I hate it, but I love pointing it out, same brand, same family of equipment, right? That's, whew, right? I'm not comparing a Carrier and a Train or a Goodman and a York or a, nope. I picked one brand. I'm not telling you who because this sucks. I picked one brand and here we are. And so you might say, well, actually, it's not always medium speed. It's whatever the manufacturer ships it at. Okay. Well, if the manufacturer ships it at, medium high, okay, cool. So 2 tons is 1,000 CFM at medium high. All right. Well, actually, not bad, right? It's actually 0.6, right, instead of 0.5, but that's a pretty good shot, right? Medium high speed was probably the manufacturer's default, great. But again, 3-ton has disappointed me, right? I'm actually getting less airflow at that 0.5. It's 0.3, right? So there's only one good rule of thumb is what I like to say. It's an annoying saying. I know I'm annoying when I do it. I apologize in advance, but there's only one good rule of thumb, and that is look it up, which is just an annoying way of saying there's no such thing as a rule of thumb or a good rule of thumb. You've got to look it up. So we're going to go through the duct design process here, and I have a couple more slides to show you, but I'm aware that this is sort of annoying, right? That I can't take anything for granted is kind of a bummer. So how I like to frame this, how I like to explain it to people is, yes, this is a little bit of work, but in addition to not getting surprised when you install something, right? Which is, I mean, I should be able to stop there, right? I mean, talk about enough reason to do it, right? We know it will work because we looked everything up. We're not going to get surprised by anything. There you go. Enough said. But take that a step further for a second. You can start really, truly evaluating what it is you're buying and what you're getting for your money when you start looking at actual performance data, right? Because, man, I have talked to a lot of people over the years who are like, we like our brand, but this unit over here, we don't sell that one. We hate that one. That one sucks. And the reason, I'm like, how'd you find that out? Oh, we put 3 of them in and we couldn't get them to work. We had to change them all out. Well, you could have avoided that step. You could have discovered that thing was no good just by looking at the performance data, just by looking at what they're, and the number of times, guys, you're paying premium dollars for a non-premium product, and they're telling you to your face that it's not a premium product. If you just know where to look, is pretty significant. And so, just to make sure you're getting value for your money, it might be worth going through the design process. So I say always read the fine print, right? Always read the fine print. So you're not supposed to be able to read that. That actually says in tiny text, you're not supposed to be able to read this, right? But they do sometimes put it in fine print. Some manufacturers are better about it than others. Sometimes they put it right in the chart sometimes. But at the bottom of the chart, they'll tell you, like, the fan coil may or may not include coil pressure loss, right? Modular fan coils, modular air handlers, the ones where you buy the coil separately, they usually don't include coil pressure loss. So you have to put that in on top of that, right? If a coil pressure loss is included, it may or may not be with a wet coil, right? This makes it really hard to do apples to apples comparisons if you don't know to read the fine print, right? Because your manufacturer say, well, our air handler is rated at 0.7 inches of static. Yeah, without a coil, right? Well, our air handler is rated at 0.5 inches of static or 0.6 inches of static with a wet coil. I will tell you what, that second air handler is way better than that first one. But on paper, if you don't know where to look, if you're not reading the fine print, it doesn't look that way, right? Fan coils might include pressure drop from strip heat. Now, usually this isn't a huge number, but it's a duct design is death by 1,000 paper cuts, right? There's just a lot of little things to take away your ability to move air, and they add up. And this is one of those things that adds up. You might find that they do include some strip heat and require additional pressure loss if you're adding more than what they assumed. Or you might find out that the air handler or the fan coil includes all of the strip heat loss. It's negligible. You don't have to count for it, whatever. And that'll be included in the blower notes. And some furnaces and fan coils, I shouldn't have wrote coils. Full disclosure, I whipped this together about 5 minutes before, not the whole presentation, but this slide about 5 minutes before we started. So some furnace and fan coils, they include pressure for a throwaway filter, which they all used to do, right? Way back in the day, there was the factory installed filter, and it always included that, or almost always included that. You should never say always. These days it's very rare, but it does happen, right? And you'd like it to be like one manufacturer always uses the same procedure. A lot of times, manufacturers will use different test procedures for their higher end products than they will for their lower end products, right? We include a filter on this one. We don't include a filter on that one, which is why, and I know it's annoying. I'm sorry. I wish I could change that, but that's why you should read the notes, man, because that's how they get you, right? We don't want them to get us. We're going to check that out. We're going to keep an eye on that. Filters. Filters are one of the things that really murder airflow. We're going to come back to this in a little bit when we do our duct design. We're going to look up our filter pressure loss. But most filter data doesn't look like this. Good filter data looks like this. Good filter data tells me what the pressure drop for a filter is at different airflows or maybe different velocities. But the majority of filter data, the majority of pressure loss from filters is a number. This is what filter pressure loss really looks like. Okay, this is, sorry, these are all missing zeros. I screwed that up. This is not what a throwaway pressure loss looks like. Put a 0 in front of all of those. Sorry about that. I couldn't copy and paste and quickly typed it out. But filter pressure loss should look like this. Okay, it should have different numbers for different airflows. And when they only give you one, which is extremely common, you're lucky if they will tell you at how much CFM, or more likely, because the way filter manufacturers think is velocity, right? So this is where they're supposed to rate it. This is the ASHRAE setting for how much they rate a filter. Most filter manufacturers are down here, right? And so this is a 16 by 25 opening. If you've got 600 CFM of air going through it, a lot of filter manufacturers, that's how they rate their filters, 200 feet per minute. So cool, if I got 600 CFM going through a 16 by 25, that's what we're rated for, right? Some filter manufacturers do a little bit better, right? They rate at 300 feet per minute, right? That's this range here. The quote unquote high velocity filters, guys, are standard velocity. I don't know who came up with the idea of calling them high velocity, but 500 feet per minute, AKA it's actually 492, but what the hell? Most manufacturers are smart enough to be like, 492 is weird. Why are we using that random number? Let's just call it 500. So 500 feet per minute is literally the standard. It's the ASHRAE standard for how much, because look, it's only 1,400 CFM at a 16 by 25, right? I mean, that's not uncommon for a filter to experience that much resistance. I mean, that much airflow, right? You're telling me 16 by 25 has to max out at like 850 CFM. I mean, 850 CFM. That's crazy. And by the way, what happens when things go way up here? Right? What happens when filter pressure drop goes up here? But I'll tell you what happens. You get a lot more pressure drop than they're telling you is what happens. And you've got this is coil pressure drop, right? And again, we rule of thumb things like, 0.1 for every blah, blah, blah. No, not even close. I mean, like, we look at some of these numbers. If I look at like some of the smaller coil, 0.45 inches of static loss. So we're gonna actually design a duct system here. So I drew up a house in Wrightsoft Universal. And we're gonna throw that puppy up on the screen here in just a second. There we go. And do an actual duct design, and we're gonna see in context what the design process looks like. So I am going to cheat here just a second. We're going to clear out the ductwork that I've already drawn. So I've done a load calculation here, and a little bit of the ductwork's already done because I wanted to be able to fast forward if and when we needed to in the process here. But so this is a load calculation. It's a nice big 2-story house. I wanted a 5-ton building, and so I went and looked up some floor plans for houses in Texas, and this is what I ended up with. And I ended up needing about a 5-ton system depending on the situation. So I've done the load. I've put the building in, right? I actually traced a PDF, which I've since deleted because, well, frankly, I stole it from a floor plans website, and it doesn't seem, I modified it a little bit, but it didn't seem fair that I should share that. And once I've laid this thing out, I put the building materials in, I changed the duct location, I put internal gains in here, and did the things you need to do a load. And we have some classes on how to do that here with RightSoft. And actually, I think we have one coming up next week. And when I was done, it gave me this estimated tonnage here, okay? And this is one of the things I wanted to sort of sneak into this little lesson here. So there's no such thing as a 5-ton house or a 4-ton house or a 3-ton house. This house has a load of 47,000 heating BTUs and 39,000 cooling sensible BTUs and 6,000 latent BTUs. That's what this house is, right? A load tells me what the house is. It doesn't tell me what equipment I need, because equipment, and we had a lesson on this one, right? Equipment is going to perform differently under different conditions. I taught a class this week. I had a guy from Arizona in the class. We looked up the performance of a 3-ton unit. The 3-ton unit that AHRI gave it a rating for, 33,600 BTUs, had a capacity in his town of 27,000 BTUs. The 3-ton unit that AHRI rated at 33,000 was actually 27,000 BTUs in his climate, in his house. And so this is going to change. And you are allowed to select within certain ranges, right? There is a trainer, I've already mentioned him once in one other session. He's under my skin. He's getting to me. But he's going around Texas and he's telling people, RightSoft oversizes. That's not a 5-ton. Add that up. That's 46,000 BTUs, right? 46,000 BTUs. You can do that with a 4-ton. No, sorry, dude. You're wrong. That's not how that works. You might be able to do it with a 4-ton. The only way you're going to know is to check. And the only software out there right now that can check is ours. So that's not true. You can check with other programs. You just got to enter the data yourself. You're going to look all this stuff up and plug it all in, and it will crunch the numbers for you. There's some programs out there that can do that. Ours is built in. So I'm breaking a cardinal rule that I have. In order to show you this, I had to pick a manufacturer. So I have 2 examples. I'm going to show 2 different manufacturers. And the way I decided is I picked the 2 manufacturers that invite me in to teach classes in Texas the most, right? So if you're mad that your brand is not on here, have me in to teach more classes, or have RightSoft in to teach more classes, and we'll put you in here. But when you do a load calculation in RightSoft, the reason, I know, you signed up for duct design saying failure is inevitable. What are we doing with equipment? What we're doing with equipment is, let's see, there we go, is duct design starts with equipment, right? There are people out there who think that you can do a load calculation, and that from there, you can do a duct design. That is not true at all. Because, and this is just my literal favorite thing to show people who tell me that, you know, RightSoft oversizes or undersizes or does whatever. This, select for manual S. So what this is going to do is this is going to look at the actual performance data for a piece of equipment, right? Data that, if you went to look it up yourself and tried to do this, data that would look like this, okay? Where you had to look up, and we did this in a different meeting, in a different session where we talked about equipment performance, but data that looks like this and tells me what the capacity of the unit is at different indoor temperatures. And, you know, AHRI rates at 80 degrees indoors, by the way, in the return. No kidding. different outdoor temperatures, so that when it's hotter, you get less capacity, and different dry bulb temperatures on the indoor, and all of this. And so we just do that automatically when we check this little box. And we bring up equipment that meets the manual S criteria. And wouldn't you know it, look at this. There are 4 and 5 ton units that meet this load. And if you're looking at that airflow column going, dude, what's the low airflow? Man, that low airflow is what's giving me enough latent capacity to keep this house dry. Okay. I did this house cheap style. Okay. Complying with the fresh air requirements, and not making the house particularly leaky. When I dump outside air from the ASHRAE 62 without an ERV or without anything else, and I compound my moisture problem there, you need to do a fair amount of moisture removal. And in order to do that, I needed needed to use the lower airflow settings to hit that latent number, right? And so there are 4 ton units that meet this load with the matchup and the airflow that we need, and there are 5 ton units that meet this load. You need to pick one of these. And so I'll pick one of these, which I've already done. And I'm gonna, maybe I can go with the 4 here. I can go with the 5, right? Yeah. And the airflow will populate. This I had to put in. This is one of those things that you have to look up. This is, here, there we go. I don't need that. I need this, right? This is where you've got to look up one of these fan charts, because right now, nobody has this from the manufacturers except for the manufacturers. They keep the data separate. So you've got to look up what fan you're using, right? You got to figure out what fan speed you want to set it at. You got to find your airflow, and that will tell you how much static pressure that fan can handle, right? So if you were here in last week's session, this is the beginning step. It's why duct design feels backwards, because you start with the fan and you figure out, okay, well, what can this fan handle? Because I'm going to design a duct system that makes that fan happy. So what makes this fan happy, right? And on a really good day, you might be using 0.7 inches of static, right? On a not so great day, you might be using 0.4 inches of static, which, again, one of the things I'm always reminding people or telling people is when you're evaluating numbers and how big is the number, right? We have a tendency to think of like 0.1 or 0.01 as a small number, right? It's always relative, okay? The difference between 0.3 and 0.7 is over, depending on which direction you're looking at it, is over 100% or over 50%, right? That is a huge deal. Okay, I could have over double. It's not 50% or 100%. Sorry, I usually use 0.3 as my example for that, and I just rattled it off as I usually speak it. It's just under 100%, and under 50%. My apologies. I am not that bad at math, but it's still a very, very large number. And so when you think about it in terms of percentages, that 0.1 becomes a much bigger deal. That 0.2, that 0.3 becomes a much bigger deal, right? So we start by determining what the fan can handle, and you look it up. That's what you got to do. And when you know what your fan is capable of, right? Because there's a lot of wiggle room. Just for the record, cabinet size has a pretty big role to play, right? Some manufacturers will have the 4-ton blower, but they'll have 2 different cabinet sizes. Right, and the bigger cabinet size is going to be the one that's better at airflow, mostly for aerodynamic reasons, right? Moving lots of air through a small space is harder than moving it through a large space, especially when that small space includes a coil. So the other thing is what kind of motor is it? UCM motor? Is it a PSC motor? Is it? But it's don't find your way down the slippery slope. Don't say, well, it's ECM and it's this and it's that, so it must be this number. Look it up, right? Because as much as I love our manufacturer partners, they will always find ways to sort of hide, a product that is a little subpar, just by putting it out there and throwing you the data and expecting you to not read it. That's how you That's how you keep them honest, is look it up. So let's assume just for a minute that this fan is, we're going to try to run this at a lower fan speed or recommended fan speed. It's not great. It's got a 0.4 inch pressure drop because I'm running it at a lower speed or whatever. To be honest with you guys, just for the record, if you wanted 1500 CFM out of a 5-ton drive, anything, it probably would be a higher number than this at any reasonable fan speed. But we're going to, this for the purposes of this design, I don't care if it's a 2-ton, 3-ton, whatever. You just got to look this number up. And I want to show you a failure, so I'm going to put a bad number in. And the lower this number is, the less power your fan has, right? The less available static pressure, or excuse me, they call it external static pressure. The less resistance, the less friction, the less static pressure loss your system can handle, the less powerful it is, right? The more friction, the more pressure, the more static pressure it can handle and still deliver the airflow that you want, the more powerful it is. So the bigger the number, the more powerful it is. The smaller the number, the less powerful it is. Kind of makes sense. So I also want to go to this static pressure page, right? So it's the next step of the design. So if you recall our thing from last week, you start with what the fan can handle. We look that up. We plug that in. Then you tell it, what does the fan have to deal with? Like, what else are we going to put in the way? Right? Well, this particular manufacturer rates their units with a dry coil, with a dry coil, and they provide a wet coil adjustment number. So you plug that in. If we were using a furnace, this number would be much higher, like much higher. Furnace coil systems, guys, they are harder to design than fan coil systems, right? There's a lot of old wives' tales as to why that might be. Put pretty simply, the air handler has one, and let's call it 1.5. The strip heaters aren't exactly big obstructions to airflow. So you've got essentially one heat exchanger, it's your coil, whereas a furnace coil combination will have between 2 and 3 heat exchangers, depending on what efficiency the furnace is. And because of that, because the air has to go through more stuff, it's just more restrictive, right? Plain and simple. So we don't have to have a heat exchanger loss because we're not using more than the manufacturer recommendation. So we're good there. But how do you know that? You look it up. It's in the blower notes, right? Supply diffusers and return grills and balancing dampers. I should actually use 0.03 for all of those. Those come right from the manual D itself. Right, so I can plug in 0.03 and 0.03 and 0.03. And my filter is going to be all over the map. If I'm using one filter, right, a MERV rated filter with, a 4-inch pleat, whatever, and I'm going to move 1500 CFM of air through it here. Actually, we have in our little, right, so of course it's right between here. So if I was using this filter, it would be a 0.1, I could be generous, call it 0.14. I could be a little less generous, call it 0.15. I think I'm going to call it 0.15 just to be safe, 0.15, right? And so what this is doing, this is calculating, it's coming all the way to the end here, it's coming up with the available static pressure. This, I love it when it comes out to 0.1. I didn't do that on purpose, but there it is, because we can do some math in our head. So 0.1. You want to do or use 0.1 on the ductulator, right? 0.1, I remember 0.1. 0.1 must be good, right? That's actually one of the ways they get you. You'll notice that filter pressure loss numbers are often miraculously, gee, I wonder how, 0.08 or 0.1. Like a lot of filters. How is that always the case with these different filters have different media and different number of pleats and different sizes? Geez, how do they do that? The way that they do that is they pick a velocity that's going to get them this number, right? And then they're going to say that this is the velocity we tested our filter at, if you can even find it in the documentation, right? They cherry pick the test conditions so that you get a number that you've heard so many times in your life in reference to duct design, it doesn't raise any flags, right? The manufacturers are a little more honest and use that 500 foot per minute velocity. Those are the ones that have 0.23, 0.4. So this one, actually, this is an honest number. It's only a MERV 10 filter, and it's manufactured by a manufacturer who also makes the furnaces and the air handlers. And so those guys tend to, try to make a filter. They're less worried about stopping small particles, more worried about killing the airflow. So they tend to have slightly lower pressure drops. So, but even for 1500 CFM, that's, you know, that's a decent sized pressure drop there. And that leaves me with this little tiny number, 0.1. So if you want to use 0.1 on the duculator, you need to have 100 feet of duct. That's what that means, right? Remember 0.1 friction on the duculator? Yeah, that's 0.1 inches of pressure loss across 100 feet of duct, right? So that means I can design a system with 100 feet of duct. That should be easy, right? Yeah. So some of you maybe have done this before, and you know I'm gaslighting you there. It's not going to be easy. It's not going to be easy at all, because 100 feet of duct is the length of duct, but it's also this thing over here. We're going to do this math for you. RightSoft does this math for you. But the equivalent length of your fittings is also going to be boiled into that. So the preferences page we have in RightSoft, this is something that you set up in advance, right? I've set mine up in advance. I'm going to do a sheet metal design. I'll throw a flex branch in there for my flex people on the return. You tell it what kind of ductwork you use. I'm going to use round metal ducts. I want to use standard sizes. I'm going to let the program reduce it for me. But this down here, so all right, there's a lot of buttons down here, to be sure. That's why you only have to do it once. But you tell it what kind of fittings you use. What kind of, I use this kind of elbow or this kind of. So one elbow is 25 feet of equivalent length. You eat up 25 feet of that 100 feet with one elbow. One boot is 60 feet of equivalent length. That's just on the supply. On the return, it's 20 feet. All right, now we're at 80. How about a plenum? How about a tap off the plenum? All right, there's 35. Takeoffs, anybody? Yeah, okay, could be up to 75. We can do better than that, by the way. That's just a straight round tap. Okay. So I don't know if we've been keeping track of that in our heads, but that's about 200 feet of equivalent, like give or take an elbow, right? So I'm not going to be designing a system with 0.1 inches of static anytime soon and getting good results. But let's try it anyway, because that's what this is about, right? It's about failing on the page is what I like to say, right? So we will take our little furnace icon or a little air handler icon, this is a pier and beam house, I've decided, because I don't feel like getting weird with the duct layout. So I'm just going to make it easy on myself and say that I have tons of room underneath the floor to design this duct system. I know, I live in a fantasy land. Sorry about that. But it is going to make it easier to keep this presentation short. So I'm going to draw a trunk, and I'm going to draw a trunk that kind of elbows over this way. Right? And I'm going to make these connections at nice 90-degree angles. And as I do that, the program is going to give me these sizes here. Right? And it's going to calculate. So I'm going to come over here and see, every time I put an elbow in there, I'm not doing anything. Like, I'm not using any black magic. It's I missed my connection. Can't do that. But when I draw this and this, it calculates the length of that elbow. It calculates the length of this takeoff. It calculates lots of stuff, right? So anywhere I want a duct, I'm just going to draw ducts, right? If I have a riser, I forget where I put the risers in my other design, but if I have a riser, there's a closet over here somewhere or something. All I have to do is tell this little piece here, if I can manage to click on it, that is in fact a riser, and tell it how far it goes. And then when I go to the other floor, I can run my ductwork off of here. All right, and I can have ductwork that's going up through the attic, all right, and lay that duct system out as needed. All right. So this is where I'm going to flash forward a little bit, because I'm sure this is going to be a session where we get some decent questions. And so here's one that I've already sort of laid out, okay? And if I go back to that equipment window and say that we're using 0.4 inches of static instead of 0.7, right? Because like I said, I do want this sucker to fail. There we are. And I go and look at that static pressure page where I put in 0.15 inches of pressure loss there. I'm going to see that the total effective length, this duct system, is 732 feet. That's all the elbows. And if we look at this duct system, I'm going to zoom out here. You know what I'm going to do? I'm going to hide my construction bar there, so we get a little more screen to look at. If I look at the first floor, right, maybe I'll hide the building layers a little bit. Right. So the ductwork starts underneath the blue stuff's underneath the house, going around this way, and it comes over here and then up. And then once it comes up, but I mean, if you really look at it, these are some pretty straight lines, right? I mean, I got one elbow. That's about it, right? These are some pretty straight lines. You're not doing too badly here, right? But it does take 1, 2, 3, 4. It takes 4 elbows to get upstairs, right? And at 25 feet apiece, that's 100 feet. You got to do it on both the supply and the return. Plus, you got these takeoffs. Plus, you got these boots. Plus, it adds up, right? And so this is going to experience a lot of friction from all those twists and turns and ducts. And it's going to cause a friction rate of, oh, and I didn't change both sides, did I? Sorry about that. Of 0.014. Guys, they taught you in tech school, trade school, whatever. If they taught you the wrong way, which a lot of people get taught, they taught you 0.1 or 0.08. This is 0.01, right? This is a tenth the size of, or a tenth the amount of friction that they taught you to create, because that's what's going to make this fan work. So here's the thing, right? If we look at some of these duct sizes, they're going to be bonkers. Okay, fair warning, bonkers duct sizes ahead, right? If I look at some of these duct sizes, you know, so this is 630. Oh wait, did I? I did. Okay, cool. So that's 630 CFM. It supposedly needs an 18-inch sheet metal. Yep. So this 67 CFM. Yeah, that's a 7-inch sheet metal. That'd be like an 8-inch flex, right? Maybe even a 9. This 400 CFM return is calling for a 14-inch flex run, right? So is this 400 CFM return? Right? This is some crazy sizes, right? Well, those are the sizes you would need if this thing was going to work. So this is a failure, right? And we agree with you. The software agrees with you. When this thing here says less than 0.06, it's saying that your friction rate is too low. It's saying your ducts are too big, right? You didn't need the computer to tell you that your ducts are too big, but it's agreeing with you. Hey, these ducts are too big. They don't even technically work. You got to do something, right? So what are we going to do? Well, that's where it becomes a little tricky, right? You could try to use, quote unquote, the Manual D suggests that you use better geometry. Better geometry would be straighter lines, which would be basically saying, essentially, this is the soffit fight, right? This is saying, I can't go up and over and around. I need to go through. It's a straighter shot. There'll be less of these things, right? This is what's causing all the restriction. I need fewer fittings. I need to go straight lines. And so the straighter my shots can get, the better the lower this number can be, and the better everything is. The problem is a lot of times the layout of the duct system is very largely determined by the builder, right? By the house and where they'll let you put stuff. So, for goodness sakes, I put the mechanical room in the middle of the mechanical area. It's not a room, it's in a crawl. But I put it in the middle of the house, right? We're never that lucky. We're always putting it somewhere over here and have to go, even further and even more around the world, right? But if I could use straighter shots, I should. So better geometry is one thing. More aerodynamic fittings. We might be onto something there, right? If I'm using these straight round taps here, right? It's just a round-to-round connection. Boom, boom. And I switched them out to saddle collars so that they had a transition to them, right? They start off wide and then they narrowed in. And I select those instead. Let's see, I may have to refresh the design. That might not have been my problem. We'll take a look. Let's see. One of the things our program can do is show the longest run. We're going to turn that on. Yeah, big surprise. It's the one with all the elbows that goes upstairs. Okay. So, and that one's at the end of the, of course, yeah, that one's at the end of the run. And so it does not actually have a lower equivalent length because it's at the end of the run. All right, well, that didn't help. Let's see, what else could we could use better elbows. I could use better boots. I could maybe do a better takeoff with a transition. And any of those better fittings. And actually, you know what, I kind of like how this is working out. Yeah, it dropped my equivalent length a little bit, you know, not much. So that's not helping me. And oftentimes it's not gonna, guys, right? I would highly recommend for simpler systems, especially using, you know, saddle collars and not using bad fittings. But you can only get so far when the real problem is the actual length and distance and turns of all these runs, right? And so what it then boils down to, right? Think of this as two sides of the equation. There is the duct and the duct sizes. So I can keep making these ducts bigger and bigger and bigger, only to a point. Then they get too big and it's not going to work. I could try to make the thing more aerodynamic, but you know what? If you're going to run your ductwork around the world, there's only so much you can do, right? At a certain point, you're going to have to attack this side of the equation. Meaning, how powerful is this fan? How much are we asking it to deal with that's not ductwork? So, is there a less restrictive filter? I mean, there is. It's not going to do as much filtration, right? You could also do a two-sided return. That's a big one, right? Single input intake returns, even in horizontal applications, aren't awesome. You know, the more intakes you have, the more surface area of filter you can get, right? And so I could start looking at that filter area. So like if I was only putting in 800 CFM to each side and I went with two of these, it would drop my pressure drop down to 0.04, right? We'll call that 0.05, right? And by bringing that up, it brings my friction rate up, and it's still way too low. So I try to reduce pressure anywhere else. Well, there's nowhere really else I can reduce it, right? These are all pretty low numbers. I mean, I can get rid of balancing dampers, but that's not going to do a lot, right? I need my strip heat, right? So I can't really deal with that. Or, excuse me, that's not strip heat. The coil's going to get wet. I can't prevent that. So at some point, it might be time to maybe consider a higher fan speed or literally a better fan, right? Maybe the fan that I chose is not going to be able to do this job, right? So this can run into trouble where you're dealing with a builder who's spec'd what type of fan they want you to use, right? We buy our, you know, products from a, you know, national organization, and, you know, we buy this one. This is what we put in every one of our houses. Well, it might be possible to go to the next blower size up from that same family. And when you do that, right, you ever wonder why they match, you know, 4-ton blowers with 3-ton condensing units, right? It's not so you can move 4 tons of air. It's so you can move 3 tons of air through, you know, more restriction. But, you know, depending on what type of fan I have and what the quality is and what I'm looking at, it could be possible that I'm looking at just going to a higher speed, right? I can get more airflow. I just got to move this up a different tap, right? Use the high tap, use the medium high tap. And so if it turns out that I can deliver this airflow at, you know, 0.6 inches or 0.7 inches of resistance, right? Oh, so close, right? So the heating side is okay. The cooling side is right on the bubble, right on the mark, right? So I mean, we really don't have to go to we'll just go to 0.65, we'll say, right? So here's what I need you to understand. You do this, there are consequences, right? You do this, what happens is that you're moving up on the fan chart, right? You're getting less airflow the higher that number gets, unless, right? So if I just stay in this one row, I'm just getting less and less airflow as I go up, unless I go up a speed, right? And now I go up and now I'm getting more airflow until I start to get less airflow again, and I gotta go up a speed. And so I can find the spot, the sweet spot, where I'm getting good airflow, right? I'm getting okay duct system. And by the way, this is just okay. This is like the minimum. And the fan will actually work, right? The fan will do what I need it to do. Now, I had to go with 2 filters. I had to go with the next fan size up or the highest speed tap or whatever. But this is what it took to do this design, right? And now that duct run, that 67 CFM, is a 5-inch duct, the way it should be, and not a 7, right? That this is a 10-inch trunk, and this is a 14, right? And not an 18 and a 14, right? And so it gets it into a range. Now, if you're really a dyed-in-the-wool 0.1 on the ductulator kind of a guy, let's talk about this a different way for a second, because having RightSoft just at my fingertips here does open up some possibilities. So in the cooling season, if you were using 0.1 on the ductulator, in here, I'm going to do 0.9, 05 or something just to get it there. So if I'm using 0.9 on the ductulator, and I just size my ductwork at not 0.9, 0.1 on the ductulator. If I use 0.1 on the ductulator, the thing they taught me to do, and I install this system the way it's laid out here, I could expect about 0.9 inches of static pressure between supply and return if I tested the system in the field. No one wants to see that. That doesn't work. That's not an acceptable situation. We have an airflow problem now that we're going to have to try to relieve. We may have to replace the fan. We have an issue, right? And what this tool does, or what any tool does, what a duct design tool does, I'm not here to, yeah, buy our software, great. But do a duct design, do manual D, right? Because I don't care if you're using pencil and paper. When it fails on paper, it's going to fail in the field, right? And it doesn't cost me anything to change the furnace now, right? It changes the cost of the price of my bid, but it doesn't cost my company any money in change outs and callbacks and any of that, right? So maybe the fan that the builder wants me to use doesn't go higher than 0.5 inches of static. This will happen, guys, right? We're at an impasse. We can't go higher than 0.5. My friction rate's no good. We're already using 2 filters, which they don't like. Like we're button heads, right? I can't make this work the way they want, right? So that might be a situation where you try everything you can, you put it all together. My suggestion is every time you hit a failure, print it. Print it and identify why it failed. Print it and show why it failed. Because if you are going to butt heads, and I don't know what your business is, some of you are inspectors, some of you are HVAC professionals. We're all kind of different animals here. Maybe some of you are even builders. But for those of you on the HVAC professional side, you can face a lot of get it done, right? You can face a lot of I just do it. And over the years, many HVAC professionals have been down this road of, man, I've been doing this for X number of years. I've put in 3 or 4 systems just like this and they don't work. So we don't want to do it. And the builder comes back with, well, we'll find somebody who will. And that's that. And that will still happen. That can still happen. But you can change the nature of the conversation a bit. If every time it hits a wall, you print, and you print that duct report, right? And maybe you print the duct drawing just for giggles, right? You print it out from RightSoft, and we'll just do one system right now. And we'll just say, and then just take a highlighter and you just say like right here, that's no good. That doesn't work. Right? Here's why that failed. Right? And frankly, it's not about the page. It's not about the numbers. It's not about even having the person you're showing it to understand why. Right? It's about showing that you did the work, you did the math, and this is where it failed. Right? And this is the reason it failed. And you know why, and you demonstrated why. But you're not telling them it's because you've been doing this for 30 years. Right? It's not because you've done 3 just like this last year. It's because we ran the numbers and it doesn't work. There's a term I'd like you to learn. What this is, and this is a dirty word in some circles, but it doesn't have to be, right? This is value engineering. That's what they call this, right? This is where you do what you can to make things as cheap as you can for the builder, up to the point where things stop working. And if you come to the table using that sort of terminology and you try everything you can with that one system, and then you try two systems, which is what a majority of HVAC professionals would want to see. It's what, as a homeowner, I would want to see in my own home if I had a big 2-story house. Is the load low enough to technically do it with a 5-ton? Sure. Are you going to give me the nice straight clean lines I'm going to need to move 5 tons of air through this with the fan you want to use? No? Well, then it doesn't work. Because a 5-ton system isn't a magic box that does that much cooling under all conditions. You need to have enough airflow. It needs to work. The whole thing needs to work. And so you try and you try and you try, and then you split it up into a couple of systems, right? You pick out a couple of different pieces of equipment. We have a tool that just, you take the same house that you did and you break it up into a couple of different systems. You got an upstairs system and a downstairs system now, right? And, we'll design this thing around 0.5, but because the layout doesn't have to go from one floor to the other and doesn't have to have all those elbows, we significantly reduce that part of the equation, right? And so even if I put that up here, we're still well within, right? In fact, with that 0.1 pressure drop on the filter, right, if we convince them to go lower pressure drop on the filter, look where we're at. We're at the 0.08 range. We're at that sweet spot that some of you got taught in trade school, right? It's not a bad number. It just doesn't always work, right? It works some of the time, but you have to work at it to make it work. You have to do the math. You have to figure out, can my fan handle this? Is my filter going to murder my airflow? Is my coil going to murder the airflow? Is this path straight enough through the system? And you can figure literally all of that out by using a piece of software or just by doing manual D, right? Like I said, pencil and paper, I don't care, right? But if you're not doing the legwork and you're not doing the math, what ends up happening, right, is the thing I was showing you before. That is not the right button, Alex. Let's try that one more time. What ends up happening, right, like all equations, right, you can have one or you can have the other. Okay, so this is this is what I'm going to fix. This is what I'm going to use 0.1 on the duculator. That's it. That's all I do. It's never failed me before. Okay. Okay. Nope. 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 There you go. Cool. 1 inch of static on your nice new variable speed fan. That won't sound like a jet engine and be dead in 3 years. Yay. If you decide you're going to do this, this becomes the variable that you're not in control of anymore. And this is what you get, or can get, right? Or you can have those 2 split systems, the one upstairs and the one downstairs, and it can work better, right? But what filter did you use? And all right, I could go through the cycle again, but I think I've proven the point. You're not dealing with the same thing all the time. Even when you think you're dealing with the same thing all the time, remember, you just change a tonnage. Same family, same brand, same everything, different tonnage, and everything goes different. Everything goes crazy, right? Same filter, different airflow, big difference, right? The same coil, where's my coil? Is it really the same coil? How much air are you moving through it, right? Shoot, like just look at one of these real quick. If you do furnace systems, right? 2.5 ton, 1,000 CFM, 0.39 inches of static. 0.5 is considered nominal, right? It's 4/5 of the system's energy going to the coil. Like, wrong, right? Go to the 2.5, 3 size. Okay, maybe that'll work, right? But this one's the one that fits on the unit nice and snug. Yeah, well, it's also the one that murders the airflow. So, yes, the manual D process can be a little tedious. Yes, you have to look a bunch of things up. No, you don't have to look them up from scratch every time. It's not like I gotta search a website every time I do it. Save it on your computer, put it in a folder, and look at them. It's not that hard, right? Shoot, do what I did. Put them in a slideshow. Just I don't care. It'd be a weird way to do that. But put them somewhere. You just keep them organized. Put them in a spreadsheet. Put them in a note. I don't care. Put them in a folder if you're a paper guy, right? But have it handy, because there's no such thing as a rule of thumb. There's no such thing as like one, like this is what coils do. No, all over the map, big numbers, little numbers. It depends on how you match them up, right? All over the map. Depends on how much airflow, right? All of them. If you start talking about different brands of filters, don't even get me started. It just drives me nuts. All right? Different manufacturers, different fine print. So you look it up, you go through the process, you find out what it gives you, and if you don't like it, change it. Work at it. It fails, fine. It failed on paper. That's a win, right? Because it could have failed in the field, and that's what we're trying to avoid, right? Okay, do we have any questions? Do we have anything people want to see? Do we have anything like that?
Everybody must already be on vacation for their Memorial weekend. Just so you know, if y'all do
notice we have like a half attendance on this one. I did notice that.
Yeah, everybody's probably checked out. But Mariel will send Alex's contact information with the course evaluation. So if you do think of something to ask him then, feel free to reach out. I had a couple. Is there a resource that you can find a real pressure drop on filters, or is it just based on how they tested it at X velocity, so there's no real tell?
So it depends on the filter manufacturer, right?
Okay.
So one thing that most filter manufacturers will, if you know who to ask, right, can probably find actual chart data, right? I have some from Flanders. I have some from Honeywell. I have some from the one from Carrier, and another one from Train. I have the Honeywell replacements for Train. Like, I've got a few of them kicking around, and several of them have. So like at its not at its worst, at its minimum, I would say you can get something that looks. Let's see. Like this. So you've got to literally like find where you are,
find it on the chart.
But it's it's not rocket science, right? It's there, right? So this is Honeywell, and Honeywell has this, but if you don't know where to look, the Honeywell one that you will most likely find on the internet is this one, and it keeps opening on the wrong screen, but it just gives you one CFM number, right? Now they give it to you at 492 feet per minute until they don't, right? I got to give credit to Honeywell. They did not put it in the fine print. They put it right there next to the text. It said, we changed the CFM, but it always, I always throw this up in my classes and make fun of them a little bit, because you're saying, oh, hey, this one has a lower pressure drop. That's like saying this car has better gas mileage when we drive it downhill.
Right.
Like, you drove it downhill. That's not useful.
Well, then again, it says it can last up to a year. I guess as long as you don't turn your air conditioner on, it'll last up to a year.
Yeah. Well, I mean.
One more question that I had, just in looking at the different fan speeds and like the medium high, typically the default, or just for my own, are there pros and cons? I mean, you're going to remove less moisture at a higher speed, but I'm assuming there's an energy penalty at a higher speed. Is there a kind of a sweet spot of a fan speed that you want to stay within, or is it just dial it up to whatever you need?
So I'm going to chicken out on this one, straight up, and defer back to my favorite refrain: manufacturer recommendation. It is. So with variable speed technology, the ACCA has a recommendation that you not exceed 70% of the maximum static pressure rating of a variable speed fan. And the sort of hard cap. I'm not sure if that's an ACCA recommendation or a Hank Rotowski recommendation, which is, he's the guy who wrote the manual D, so kind of the same thing. But 70% of but otherwise it's, I mean, if you go to your, remember your low load homes presentation that John Sedin did? Yeah. He's designing variable speed fans at very high statics in order to deliver good velocity at his registers. So I mean, it's there's a lot of give and take. I mean, good Lord, the HVAC industry is all about give and take, right? Pros and cons. You do this and this goes, it's like you push down on this end and the other end goes up. That's how equations work. That's how the world works. So, and I find that different focused people, different focused jobs look at things very differently, right? My energy organizations have a tendency to be like, I don't want any more watts than this out of this fan. Like, all right, well, that's great, but it's not going to move air now. So, what we're going to have to do here is we're going to have to use, 2 or 3 different units, which will now increase and then they get upset because they're like, no, well, there's more tons in this house now. So yeah, well, I had to slightly oversize 3 units instead of going with, 1 or 2. That happens, so it's a little tricky to manage, but start with, I tell people start with manufacturer default, start with it, but look at the numbers and determine what's realistic, right? Because if you take the example, where's this one, right? If medium was manufacturer defaults, right? Even if medium high, there we go. If medium high is manufacturer default, that's unrealistic, right? You've got to be kidding me, right? So, if I'm going to go to medium high and I want 1200 CFM, and I don't know if I want 1200 CFM, I might only want 1000. If I only want 1000, that's going to work awesome, right? But if I want 1200, I'm not going to be able to. It's just not enough. Like I'm going to have trouble. So I better go to high. I mean, that's at the end of the day. If you're not moving the air, you're not making it comfortable, and what's the point?
Well, right on. Well, we are right on time. 2 minutes after. Cool. I think you wrapped that series up fantastic. I'm sure there'll be folks reaching out to you. Thanks for joining us, everyone, this morning. Have a fantastic Memorial weekend, and we will see you next time. Y'all have a great day. Thanks, Alex.
Thanks, guys.